Let's start the class. It's the first time that they send us into this room and it's a little bit weird. We don't have a screen, we have nothing, and we have to improvise. Okay, we are again here with autonomous systems. If you remember, last class we did just an introduction to mobile robotics, okay? Today we want to start with the main topic of the course, that is motion planning. And we will start with the most simple algorithms that you can find in this field, that are back algorithms, okay? First of all, but I want to just introduce you a little bit this new section that we are going to start now, that is the motion planning, and present you all the algorithms that we will be touching during this course. Will be just a small introduction, and then we will go directly to the back algorithms. As you can see, we will see several evolutions of the same algorithm. Let's start. Today we will do these back algorithms. As you will see, it's quite simple algorithms. We will not ask you to implement them, although it's a good exercise. If you are not very confident of your Python skills or things like that, maybe not all of them, because there are a lot, and the last ones are not easy to implement, are quite tricky. But if you want to try for yourself to try to implement like 0, but 1, for instance, it's a good exercise for you. However, in the labs, that you will start labs today at 12 with Sebastian, not with me, you will see that the lab is not about back algorithm, it's something even easier. Okay, it's just implement a kinematic model of a bicycle-like robot. But it's a good exercise. If you want to do it, after I've explained it, in fact, during the class, you will see that I will explain the algorithms very algorithmically, like how it should be implemented. Then if you want to practice, it's a good thing for you to do. Then we will do the configuration space. If we have time, we will try to do that as today, because this is just 10 minutes introduction. It's more than introduction, is to set up some concepts, some names, some bars that we will be using during the full course. And it's important to have them clear the sooner the better. Next day, for sure, then we will do the potential functions. There is a lab related to the potential functions, and here, yes, you will have to implement all the things that we explained in the class. You will have to implement them during the labs in the future, not next week, but on the other week, in 2 weeks' time. Then we will move to roadmaps. Roadmaps, I think I already explained a little bit this during the introduction, but the idea is that when we plan, we can have already a previous roadmap. For instance, when you ask Google Maps to plan a route from here to your home in the city center, Google Maps already have a roadmap of all the possible roads and streets and highways, whatever, that you can use in order to find this path. In some other things, for instance, if we are inside this building and we want to go from this room to another room, maybe there is a roadmap with all the corridors, maybe no. Maybe there is only a sense of free space, occupied space, obstacles, whatever. And then you have to plan here. But lots of algorithms use this concept of roadmap, that there is a previous map of the environment and that you can use it in order to plan. Here, when we, in this first lesson of roadmaps, we will study different kinds of roadmaps, different ways in which we can specify this roadmap, and then in the graph search, we will see how, given one of these roadmaps, we can find the best route, or the optimal path, or the path in the fastest way, or whatever. Okay, there are several algorithms. Ones are one win in terms of performance for one thing. Some others are better or are more suitable for other things, etc. And finally, we will see the sampling-based algorithm. Sampling-based algorithms, we will see that some roadmaps, in fact, use sampling-based techniques, but there are some other sampling-based algorithms that do not rely on a roadmap. In fact, they build the roadmap while they find the path, and then they used to be very fast, because instead of requiring a very specific roadmap of all possible roads, they only look for roads in the direction to the goal. And then if the space is very huge, because they only focus on the space, let's say, between the initial position and the goal position, then they can be much faster. And then you will see why sampling-based algorithms are the state-of-the-art algorithms nowadays, although a lot of graph search algorithms are still being used, especially if you already have a robot. Okay, but our goal here will be always the same. We will be a robot, like the robot that you have here, and the robot will have to reach a goal. Okay, here I put this simple robot. Okay, and then we will define an area in which the robot can traverse, and in this area there will be free space, all these white parts here, and occupy the space. Here I just put some stupid blocks here in the middle to indicate this occupy the space. Sometimes we may have roadmaps predefined, sometimes not, etc. But this is our goal during all this part of the lesson, that will be at least 5-6 classes. Okay? Then let's start with the first family of algorithms that allow us to do that. They are called bug algorithms because they are inspired in bugs. Okay? The idea is, if you have ever seen an ant or a beetle trying to reach a piece of food, they tend to go straight. But if there is some obstacle in the middle between the food and where they are, they just go around the obstacle, very close to the wall, and when they see the food again, they go straight again. It's very simple behavior that most of the time works. And this is exactly what the bug-zero algorithm does. Then here there are some assumptions. The first assumption, that they must be true, otherwise we cannot apply these algorithms, is that we know the direction to the goal. What this means? It means that even if we don't have a direct side to the goal, we know at which orientation we will work mostly in this course using 2D robots. I mean, our robot will be, imagine a Roomba-like robot, then they can move forward, backward, or turn left or turn right. This is what we can do with our robots. Okay, then our configuration state, I will talk about that later, will be the position X, the position Y, and the orientation that, and sometimes maybe I will put theta, sometimes I will put yo. Okay, these Greek letters. Then here we need these two assumptions. First one, the direction. Let me put it in red, that maybe it will be easy to see for you. The direction to the goal. It means wherever we are, we need to know where the goal is. If the robot has its own position, because it has some of the localization algorithms that you are studying with Pera-Ridao, and the robot is able to know where it is in the wall, and it knows the position of the goal, where it has to go in the goal, is very easy to compute. I mean, if you are in a wall, although there are lots of obstacles that don't allow you to see the goal, but you are here and your goal is here, it's pretty easy. If you know your position, X, Y position, and you know the goal position, X, goal, Y, goal position, if you know this information, it's pretty easy, straightforward to compute this orientation, okay? It's just the ATAN 2. Basically, you have here a triangle, this is the increment of X, this is the increment of Y. If you do ATAN 2 increment of Y divided by increment of X, this is the orientation. That's all. This is a question that you will see plenty of times during all these courses. Then it's something that we can imagine that we will always have, this sense of direction to the world. The second thing that we need to have, let me just clean this a little bit, okay, more or less, is tactile sensors. What tactile sensors means? Again, if we come back to the most simple 2D robot that we may have, it's a Roomba-like robot, okay? The current versions of Roomba, they have lidars and infrared sensors and cameras and everything. But if you come back 15 years ago, they basically have two bumpers. And I already explained that the other day, no? If a bumper is a button, nothing else than a bumper, but with a nice chassis in the front. If the right bumper is touched, it's because you have collided with an obstacle that is more or less at your front right. If the left bumper is touched, it's because you have collided with an obstacle that is left front. And if both are touched together, it's because you are touched with something that is more or less in front of you. A little bit right, a little bit left, but almost in front of you. Then with just this very, very simple set of sensors, these robots should be able to navigate towards the goal if they know the direction to the goal. Okay, then now we have more or less the setup to the robots. Very simple sensor suite. Yes, they have these tactile sensors and this sense of the direction to the goal, and we're trying to imitate the behavior that Bugs does. You can imagine that with these very low requirements, the algorithms that we will end up are not perfect, okay? Or they take a lot of time, or sometimes they are unable to reach the goal, etc. Okay, then let's go to see them, and let's go to see which are the problems of each of these algorithms, and how each evolution in this family of algorithms try to solve one of these problems at a time, until the last one, the tangent back, it's quite good, okay? Let's start by for the bug zero. Okay, the bug zero algorithm is the most simple, and is the one that is truly inspired by a bug. Okay, it does what I told you before. It has basically two behaviors. If it can go towards the ball, and going towards the ball means that with his very limited sensor suite, that is these bumpers, if you want, instead of bumpers, you can imagine infrared sensors that allow you to see an obstacle when you are very close to it, but not when you are far, okay? You don't have to touch, but you have to be very close. Then, with these tactile or infrared sensors that allow you to see if you have obstacles around you, if there are no obstacles in the direction of the goal, you just go forward to the goal. However, if there is some obstacle in the direction of the goal, you just try to go around the obstacle. Okay, here you see an animation. Okay, I think here I have the video. Yeah, this is the video. Okay, the robot starts here on top, and then it's trying to go to this green cross that you can see down. The sooner it collides, it's in front of one of the obstacles, it just turns or left or right. This is something that the algorithm has to decide a priori, okay? And you cannot swap, now left, now right, no, because then you can end up in some local minima very easily. If you turn right, you always turn right. If you turn left, you always turn left. Then it just moves straight towards the goal. The sooner it detects an obstacle, it just, in this case, it turns right. Okay, but the moment that it seems that the direction to the goal is free again, for instance here, it believes that the direction towards the goal is free because it has only, it has only tactile sensor. Then for their sensors, there is nothing between here and here. Then it just decides to go forward. However, what happens when it reaches here, it notices that no, it was not true. It was not free. There is an obstacle in the middle. Then it follows again the obstacle and just says, okay, now my way is free again. Tries to move forward, but here again. It's the simplest algorithm that you can imagine. And here is the pseudocode of this algorithm. Okay? Implementing that, I mean, explaining it super simple. It's basically two behaviors, and with simple animation, I think all of you have get it. Implementing it, it's always a little bit more difficult. The idea is that this algorithm do not have memory. This is the idea. However, in the implementation, we need a little bit of memory. How this implementation starts? First of all, I don't know if you are very used to these algorithms. This is pseudocode, okay? This is not C, this is not Python, this is not Java. It's some generic language that is easy to be reproduced in any other language, okay? And it's quite standard. It's how in the papers, the people that write papers in LaTeX used to use this kind of diagrams. I will try to, every time that I can, put the algorithms that you will be implementing in the labs in Python in this format. Then for you will be very simple to just to take that and transform it into Python. Of course, here I always make use of some nice functions that I do not implement, and you will have to implement in the Python, then for you will be a little bit more challenging than for me. Here for me it's 20 lines of code, for you maybe it will be 100 or more. Okay, then let's start. This is the signature of the function, okay? All the functions, all the classes, all the objects has a signature. A signature means what enters to this function and what is the output of this function. In this case, the input is the configuration in the start position, must be where our robot is, x, y, theta. The goal position, in this case, the goal, we will not consider that it's x, y, theta, but only x and y. Okay, we don't care if we reach the goal facing forward or facing backward, whatever. We just want to reach an XY position. Then here it can be a little bit confusing, but well, Q star can be also XY if you want. However, we know that our robot, if it's a 2D robot, may or may not have an orientation. If we imagine that we have just a dot robot that is a point, there is no orientation, and then both Q star and Q goal are exactly the same, XY. However, if we think with a turtle ball-like robot or a Roomba-like robot, then we need somehow to manage also the orientation of the robot. Then we need a representation of the wall, because in the wall there are obstacles, you remember. Okay, the wall has obstacles. Then we need some way to define what is free and what is occupied. Here I put the simplest wall representation that I can imagine, that is just a list of obstacles. Okay. Here there is C obstacles, a list with all the obstacles. You can imagine that obstacles are triangles, or there are circles, or there are squares, whatever. But you can go through this list of obstacles, and if your current position is not inside any of these obstacles, you are in free states. Otherwise, you are in an obstacle, and you are out. And then just a small parameter here is just an error, a threshold. Okay. You can have different thresholds for different things. I put just a single threshold to make things easy. And which will be our output in this particular algorithm? Will be a path. A path that our robot has to follow. Okay, here the path is this capital P. And then it will be a list of points, in this case, because we assume that we are xy, and everything is xy, that go from Q star, from Q goal, in a more or less continuous way. Of course, although real life is continuous, when we program, we discretize things. Then there are some steps here, step towards. Here we need to move from one position to another. Here we will, inside this function, it can be also parameter that you can put here. Again, to simplify things, I not put it. But when you move, for instance, we will move every meter or every 20 centimeters, whatever. Okay, then the points in this path will be every 20 centimeters, every half a meter, every 1 meter, whatever you decide. Initially, this is the signature of the function, and this is the initialization of the function. When we initialize is that the first position that we will move at is the Q star position. Okay? And then the path will be initialized as a list with this position. This first algorithm, I go very slowly, very step by step. If there is something that you don't understand, for instance, the arrow is because we don't like to do equals to assign things. Okay? Because equal can be equal or can be assigned to. And then normally in serial code, we use the equal for equal things. Is A equal to B? And we use the left arrow to assign things. This value, this bar here, takes this value. Okay? I don't know if you are computer science, if you are familiarized with this code or not, and then is why today I go very, very slowly. This, when I put these brackets, it means that it's a list of things, a collection of things, normally things of the same type. Again, this is something that it's not directly you cannot translate directly to Python, but it means that direction is a bar that either has the value left or has the value right. Okay, this is something that probably in Python you have to do some kind of random -1 to 1 integer, I don't know, something like that. Okay. But these are the three things that we initialize: the Q, the current Q, the P, the collection of positions, the path that you will finally return, and the direction. Remember that we need to decide if we turn left or we turn right, and we only have to decide one. Then we decide in the initialization part of the algorithm. Then, while here, check also that here we don't use brackets or only indentation. We use indentation because I think it's easier for all of us to look into the code if it's indented. But this while ends here, and while this if has an else here, and here it's very clear for the loads are. Then, while the difference between the current position and the global position absolutely different, then here we have to compute square, root square of x, x qx minus q global x square plus qy minus q global y square. If all this is bigger, than this threshold that we have defined in our function, then we keep moving. We are not reach the goal. Again, we're in a continuous wall. We will never reach perfectly the goal, okay? But we will be close to it. And it's fine. You have to define this threshold. This threshold should be smaller than the step, but not very smaller. It will be around the step, something like that, okay? Because otherwise, you can just end up trying to move around the goal and never reaching because your step is too big, or you can think, it should be the same size more or less than your step. Then here again, I define a function that for me it's pretty easy, that if you have to implement it in a real robot, it can have no problems, that says, if there is line of sight between the current position and the goal, considering this list of obstacles, what this means? It means that if we have to implement this function, this loss here, what we have to do is say, okay, is the Q goal facing obstacle, facing Q goal, let me try to draw it. If we have here our Q goal, and let's put it like an a star better. And we are right now here. This is our Q. Okay, then this is our direction, no? We are facing this direction. Maybe we have an obstacle here in our list of obstacles, then because in the direction of Q goal, there are no obstacles, it's fine, I can move. However, if I have also an obstacle here, because in the direction of the Q goal, I see an obstacle, I don't have line of sight. Okay, then this function, line of sight, returns true or false. It's the only thing it does, depending on where we are facing, and where are the obstacles around us. Okay, this is not super easy to implement, but it's not super complicated. You can do it, I'm sure. Imagine that, yes, we have line of sight, and this obstacle is not here. Maybe there is this obstacle here to the right, but not this obstacle in front. Then we step towards the goal. We just move. What I tell you is, I put here some dots. Every dot maybe it's 30 centimeters, maybe it's half a meter, and we just move from the Q to the Q goal, and this generates a new Q position. Then this new Q position has to be appended. And it's normally what we do in order to make this list to grow, okay? Then we append this new position here, then here we will have the initial position, the Q star, then we will have the new position, etc. However, if there is no line of sight, for instance, in this situation here, then what we do is, and this is the trick that I tell you, this algorithm should not have memory. However, we need to remember at which point we have hit the obstacle, just because it's possible that, imagine that there is something like that. Okay. We start here. It's impossible from us. Imagine that we cannot escape here. We start here and we will reach this position. In this situation, we will move here. We will go around the obstacle. We do it here with a different color, no? Blue means we will start here. We will move around, and come back here. If we don't store this hit position, we will be here forever, looping forever. Okay. Then this remember hit point, it's something that we assume that bugs are intelligent enough to not stay forever making loops here. And then we just remember this position, this dot here, this blue dot here should be the hit position, and then we start following the bouldering to a specific direction for a specific step. Okay, the step probably will be the same distance that we use here in the step towards. and the direction then can be left or right. Here I turn left. You can imagine that is left, but it could be right. It's exactly the same. Every time that we start following the direction, we append the new position to Q. But if after moving forward we gain line of sight, then we reach to a situation in which the new step, the new position has line of sight to the goal, then we just break. We just stop this repeat here, this repeat until we just break that and we come back here. We check if we are already in the goal. If not, if we have line of sight, we should have it, because if we have entered here, it's because we have line of sight, then we move forward, and that's all. And this will be continuing forever, except for two things. One, that we reach exactly the same position, then the current position is equal to the peak position minus the delta. Here is where you have to be careful if you want to implement that. If this delta is too big, the first time that you move, you will be inside delta, and then the first time they will tell you that you are in the same position. You have to manage that, okay? Here I just put a very simple version of the code, but this is something for you to fix, let's say. Maybe just having two different deltas is more the second thing is that if you break this loop and you go to the other loop, at some moment, your position will be more or less the same than the goal position, and then you will stop. Here you will stop because of a failure. Here you will stop because everything has worked, and then you will append the final position to the Q goal, because the position that you have reached is not exactly Q goal, is Q goal minus Q more or less smaller than this threshold. Then to have exactly the Q goal position, we will append it in the end, and then we will return the full. Okay? And this is the full back zero algorithm. As you can see, there are some tricks here in the line of sight, some tricks of how to follow the boundary that are not specified here. And then if you have to implement it, it will take some time for you, I'm sure. But it's not a difficult algorithm to implement, and although it's very easy to explain, it's not so easy to implement. Okay? Let's now practice a little bit. Okay, imagine that we start to the red position and we want to reach doesn't matter the color, and we want to reach the green star. Imagine that we have selected, I don't know, left as a direction. Okay, then what we will do is try to move straight, okay, from here to here. Okay, you see my cursor. Then I move around here until I found a wall. When I found an obstacle, a wall, because my algorithm told me to move left, then I move left. And I keep following the boundary until I have visibility. See that here, for instance, I still do not have visibility, okay? Because visibility, this is the line towards the goal, and it's crossing the obstacle. Then I don't have visibility here. I have to keep continuing until I reach more or less this position. At this position, yes. Here, I can move toward here. But what happens that when I reach this point, I realize that there is another obstacle, and I stop. And at this point, because I'm commanded to always turn left, then I turn left again. I turn left, I move till here, and when I'm here, I can finally reach the goal. Okay? Try to do the same version, but for the right side. I give you just 1 minute for you to think the one in the right before I do it here in the screen for you, but try to think how you will manage to do it. If you have the slides, try to draw it. We will start exactly the same way, no? We will move around here, but this time, instead of left, we will turn right. We will turn right. And the same, if at this moment, for instance, we try to move to the goal, we are crossing a wall. This is not good. then we cannot do it. We need to wait until we are here. At this moment, yes, we can move towards the goal, more or less, something like that. And in this moment, we need to turn right. Turn right, we keep following the obstacle, we keep following the obstacle, we keep following the obstacle until we are more or less here, and then we reach here. Which is the best path? The red, the blue? Probably the red is a little bit shorter, no? But you never know that, okay? You have to select one at the beginning and stick with it. But both reach the goal, then it's fine. What happens here? Try to do the same here. Let's try to do the same here. I will start, I don't remember which is the one that works better. I will start with the blue one, okay, the red one. Okay, here we move towards the goal. And the sooner that we found an obstacle, we start moving around the obstacle. Okay, I don't have a very good pulse. As you can see, I don't have yet visibility to the goal, but at this moment, yes, I have visibility to the goal and I can reach the goal. Okay, it has been not the fastest path for sure, but I've reached the goal. What will happen with the other one when I decide to turn left instead of turn right? If I decide to turn left instead of turning right. Let's do it. I will start exactly the same, going towards the goal. I detect my line of sight returns false, then I decide to follow the boundaries. No, sorry. At this moment, no. Oh, sorry, this is wrong. At this moment, I have visibility, then I have to turn this side, more or less, okay, because I have visibility towards the line of sight. Then I turn here, and then I start following it. I'm just following the boundary of the obstacle. I turn it. Okay, is this the hit point in which is this the hit point? No, the hit point is not this one. Is this one? Then I just continue. I don't know why that's done. Here, I go here, and then I see, okay, I have visibility again. Oh, sorry. Oh, what I've done. I've jumped towards the end of the session. Sorry. It's bug zero. Okay. Okay, sorry. Then in this moment, I reach exactly the hit point. You see? I've done a complete circle until I reach this point here. Then this is the hit point. Okay, then if we remember in the algorithm, it says that you repeat until false, follow boundary, but if your current position is the hit point, or more or less the hit point, you return a failure. Then what has happened here? That one side has returned us the correct path, maybe not the best path, not the optimal path, but a path. If we decide to turn right, but if we decide to turn left, it ends up in a loop that we cannot fix it. Every time that we have something like that, if it turns right, this spiral, the spiral turns, it turns left, then if we turn right, it's working, and if the spiral is the opposite, if the spiral turns right, then if we try to go right, we will end up in a loop, and if we move left, it will work. This will happen always. Okay, then what can we say from this algorithm? Is this algorithm, there are lots of terminology in all the courses that you will be doing here. Some of the things that we need to analyze for all the algorithms is the algorithm optimal? It means, is the path that this algorithm returns to me the best one ever? That is impossible to improve this path? It is figure that it's not, okay? It gives us a path most of the time, but it's not the best path. Is the algorithm complete? And complete means if there is a solution, even if there is only one solution, the algorithm will find the solution? Not again, okay? Because we have seen that sometimes you found the solution, sometimes not, okay? If I was, I don't know if I will be able to draw it, but if we have something like that, this is a spiral rotating right, and no, sorry, let me do it a little bit different. And then here inside, I do a spiral rotating left. This will have no solution at all, okay? Because if I always turn right, I will get looping the first one, and then I will be looping the second one. If not, I will be looping the second one because it's one inside the other, and one is facing one direction, and one is facing the other direction. Okay, just for you to get the idea. This. Yeah, sure.
At that point, the collision point can't be changed just the direction to the other side.
This could be done, for instance. This could be done and try to see if just changing the direction it improves. Yeah, this could be, for instance, one possibility. The back algorithm, the back zero algorithm, the side says that no, that when you reach a hit point, it's a failure and it finalizes. But now we will see 3 more algorithms that propose changes, not this one, but yeah, this probably will change. I've not done the study of to see if it's at least complete. I mean that if there is a solution, it found a solution, but yeah, it's something that maybe it may happen. Okay, let's move to the second algorithm, the back one. This tries to improve over the back zero, adding memory. Okay, I tell you that back zero has no memory, although we put this hit point that is memory. This includes memory. And here the idea is similar. We start just facing the wall, but the sooner that we've found an obstacle, instead of just go around the obstacle until we have a direct line of sight towards the goal, in this case will be around here more or less, instead of that, no, we just circumnavigate the full obstacle. And for every point, here we not only have the heading towards the goal, but the distance towards the goal. Okay, we have these two concepts. Again, if we know where we are and we know where the goal is, it's very easy to have that. It's just a model. Okay. Then for each point, for each step that is doing around the obstacle, it measures this distance, and then it stores at which point in the border, in the perimeter, of the obstacle, the distance is smaller. And whenever it has done that, then it just, when it reaches again the initial point, then it moves for the shortest path because it already knows if it's shorter to reach this point from the left, from the right, here you have done the full perimeter, and you have this information, then it moves towards the position. Here I put also a video. Okay, it's moving all around the obstacle. Here I do a little bit of it should have moved toward here, and I just jump towards the minimum position. This is my implementation, that it was very fast. But the real algorithm cannot jump from here to here. It has to follow again, and then you do the same for this one, the same for this one, and here you will see that whenever it has found that, it says, okay, this is the shortest point, then I will reach it. The only problem is that in this implementation, that it jumps to the shortest path, and it should move when then you do some exercises, you will see that we move really towards the smaller. This algorithm is much slower. Tell me.
But when after reaching the first point, after circulating
yes,
he will decide to move left or right, or left or right, or
it can decide left or right because it knows. For instance, from here, it's shorter to move right, according to the agent, that it moves like that, to this point than left, because it has memory. Then it can measure distance toward the goal, and for instance, how far am I from the initial point? And then if when you reach again the total perimeter, if you remember how far you were from the initial point when you have measured this distance, you can decide if it was easy to go through the same direction, for instance here to the left, or through the right. I mean, to start the circumnavigation of the perimeter of the obstacles, yes, we decide if it's right or if left. This is something that we have to decide at the beginning. But then to reach again the smallest point, no, you can decide left or right because you know that you have already done the full perimeter. Then it's some information that you have. Okay. Then this is another algorithm. What are the benefits or the problems of this algorithm? Okay, let's see first if you want the algorithm. I will not go as detailed as before, but we have the same input, the same initialization, and the same condition. Well, we have not reached the goal, then we just operate. If we have line of sight, we do exactly the same. We just move forward and append the new position. However, if not, what we do is we record not only the hit position, but also the minimum distance, okay? The beginning, the minimum distance will be the distance, the d-min, okay? Okay, two things. The minimum distance between the current position and the goal, if it's the minimum, of course, the first time for sure is the minimum because there is the only one that we have, and where we have computed this d-min. Initially, we have computed this d-min from the hit position, okay? But then, when we start following the boundary, we store these positions, and then if the distance from the current position to the goal is smaller than this minimum distance, then we update these two values here. We update this minimum distance, and we update the position from which we have computed this qubit, okay? Is this clear? And then we do that until we have reached again the hit position, the initial position. We have completed the full navigation around the obstacle. Then here, while Q, while we have not reached this position, the position QB, what we do is we follow the boundary through the shortcut direction. Okay, you can also implement that, also following for the same direction. It will be not so efficient, the algorithm. It will work. It will work exactly the same. But if you have something that confuses you, which is the shortcut direction, then you can do it. And here we don't have to do nothing. Just append every time that we move again. Remember, imagine that we have here the obstacle. Let me do it in red. We have started from here. We have circumnavigated the whole obstacle. And because our goal was here, this is the starting position, we know that this is the minimum position. Then when we reach this point, we need to move again till this position. Okay, and then we can move towards the goal. Okay, then the path will be one full perimeter plus, not half, but almost half perimeter here. Okay, this is what we are doing, is this half. And that's all. When this finalizes, we can move again to the line of sight that will move us towards the goal. Let's try to do it, okay? It's the same, exactly the same environment that before. Here doesn't matter if I start left or right, okay? Then I just move toward the goal until I found an obstacle. The moment I found an obstacle, I circumnavigate the full obstacle. And when I reach this position, because at every point around this obstacle, I measure the distance, which is always the closest distance between 2 points, the straight line. Okay, then the straight line will be here, more or less. Then I have to reach this point. I don't know what is shorter, probably left, no, it's shorter. Then when I'm here, when I reach again the hit position, I move towards the Q-min position until here, and then I can move forward again. And when I reach this position, I found another obstacle. Then I have to circumnavigate again this obstacle. This is a tactile sensor, then it should be very close to the wall, but sorry, it's very difficult to read here. Here, what is the minimum distance? Probably the minimum distance should be something like that. Then if the minimum path is moving right, maybe, yeah, I'm not 100% sure, but probably. I will reach this point and then move right. Okay? If I do it starting circumnavigating for the right instead of the left, I will obtain exactly the same. Okay? More or less, this is what the back one algorithm will provide us. let's see what happens with this algorithm. Okay, here remember that the previous time we have problems. If we try to reach the goal from this position, sometimes we reach it, sometimes no. What do you think that will happen now? Let's check it. Imagine that we start for the left. The left was the one that crashed there before. Then let's start for the left. We move here. We move here. Now although we have line of sight, we are not jumping. Okay, we are following all the perimeter, all the boundary of this obstacle. All the obstacle. Here we are super close from the wall, but we are not jumping. Follow all the obstacle. All the obstacle, all the obstacle, all the obstacle, until we reach again the initial position. And here we say, where is the closest point? And probably the closest point is this one. Then how we reach again this position? I think that from the left, no? We move here, 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 and then we just move towards the goal. Is this algorithm optimal?
No.
It is not. Okay, it's super slow, but it's complete. It is. Okay, and it's important. Sometimes it's better to reach a place that maybe they taking more time than necessary, but to be sure that you always reach the point. Okay, then this is one of the advantage of using the back-one algorithm, that it is complete. Okay.
What result of the code is already in the line that we was to scan all the obstacle. While I scanning the obstacle, I reach the goal.
If scanning the obstacle, you pass on top of the wall, of the goal, or something like that. Yeah, it may happen. According to the algorithm, you should do the full algorithm and say, yeah, there is a point that is a distance 0 from the goal. With this point, this is the minimum that you can reach. This will, if you follow the algorithm, you should be that. Of course, then you can do lots of improvements in these algorithms. As I tell you, right? These are not the algorithms that we want to implement in the end, because they are quite old algorithms that they can still be worth for something, especially the last one I will introduce today. But there are other algorithms that are much more powerful nowadays. Just another concept that is very interesting when we see to the algorithms, that is the order of magnitude of things. No? And for instance, in path planning, what we are interested sometimes is in the bounds of the algorithm. For here, for instance, the upper and the lower bounds of the path. Okay, this means how long can be this path and how short it can be this path. No, the maximum and the minimum length that I can take. If I have no obstacles at all, the robot will start here and just move straight to the goal, and I will obtain the shortest path possible. That is the straight line. That is this d distance, the distance between the wall and the starting position. Then my lower bound is d. When I have no obstacles, my path will be distance d. However, when I have obstacles, because at least I have to go through the perimeter of the obstacle 1.5 times, because one time, and imagine in the worst case possible that I cross, imagine that I'm starting here and the goal is here, I have to go exactly 1.5, one time, and then because this is just in the middle of the obstacle, and a half. This is the worst case possible, no? The best case possible is that I'm here and the goal is here, and then I cross the obstacle here, I just go one time, but then I just realize that I have to do one and almost nothing. Then every time I will go between 1 and 1.5 times around the obstacle, then the worst case possible is 1.5 plus for all the, we add all the perimeters of all the obstacles and we multiply by 1.5. Okay, it's easy, no? Here and okay, what I told you, it's a back one complete. Yes, it is. Is the back one optimal? No, it's not. Okay. Okay. Let's continue then. We have seen back 0, that is more inspired with the real back. We have seen back 1, that is an improvement of this, that of course it's not as close as the real back behavior. I've never seen a nun doing a full turn around an obstacle before going to it. They are much more clever. And then there is the back 2. Back 2 tries to keep a little bit the good of one and the other, no? Back 0 used to be more fast most of the time, although not optimal, at least to be more fast. But back 1 was complete. And let's see how back 2 tries to keep this completeness, but making it a little bit faster. Okay, the idea is that it generates this extra line at the beginning, okay? This is an imaginary line, okay? It's not that it's tracing a real line in the environment, it's just, this is the line that it wants to follow. Of course, we know that the straight line is always the best way to reach a goal. Then it says, okay, this is my goal, is follow this. And then, if an obstacle is in the way, it follows it, it just follows the boundary, like in back 0, back 1, until it encounters the M line again, but this is very important, and this is why I marked you in bold, closer to the goal. Okay, what happened? If here I do some kind of a strange loop, and I met this blue line of M line, farther from the loop than the hit point, than this point here, I'm not going to follow it. Only I want to follow the M line if I found it again, and it's closer to the goal than the hit point. Okay? Let's do it again. Small video. Yes. Let's see if now works. Yeah. Okay. The line is always there. We just keep following the obstacle until we reach again this M line. It doesn't matter if we have a line of sight with a goal or not. The only thing it matters is that we reach again the M line in order to move towards the goal. Okay. With that, you can see that it's faster than the back 1. Maybe it's not as fast as the back 0 for this wall that is pretty simple, let's say. But let's see if it is able to keep this completeness property that we have with the back 1 and that we didn't have in the back 0. Okay, first of all, the algorithm, the pseudocode of the algorithm. The beginning is exactly the same except for this M line. Okay, in this M line, we define the line that goes from the Q star to Q goal. Okay, all the points that are in this line. The initial part is exactly the same. If we have line of sight, we move towards it. And if we don't have line of sight, we store again the hit point. We need to store it. And then we start following the boundary with the direction that we have chosen, either right or left, adding the new points to the Q. And then if we are on the M line, and again, this is the very important condition, and the distance of the current position, Q distance, Q is our current position, then the distance from Q minus goal brackets, the modulus of these two vectors is smaller than the hit point and the goal, then we are closer than we were in the hit point. Then what we do is we just break this follow boundary and we go again to the line of sight. We keep again doing this other behavior, okay, moving towards the goal. Otherwise, if this is, and this is being repeated all the time until we reach the hit position. If we reach the hit position again, it may be a failure here. If we reach this point here because we have reached the hit position, yes, then it's a failure. What this means that imagine that for any reason we have not found, in this case it doesn't happen. Let me try to draw something here. That we are inside the box and we want to reach this point, and then we just go here. This is our M line. Okay, we just start following the M line, then we reach the hit position, we do it, we follow. Here, maybe we have crossed the M line again, no? Because in fact a line is infinite, then we has crossed the M line again, but here we were farther than here, then we are not following the M line in this point. We just keep following, and then here we reach the hit point again. We reach the hit point again, then there is some problem, there is a failure here, okay? Then this is this return failure that you see here, return failure. Okay. Let's see how it behaves with the standard example that we have done. Let's start moving right. We will draw the M line. The M line will be always the same. Then I draw a different color. This is our M line. And then if we try to follow it, we just follow towards the goal, that is following the line. Then we just keep following the boundary of the obstacle. Here we have direct sight, but line of sight to the obstacle, but to the goal, sorry, but we are not following it. We keep following the obstacle until this point. In this point, we have reached again the M line, and we need to compute if this distance to the goal is smaller than this distance. If it is smaller, if this case is smaller, we just go towards the goal that in the end is following the M line. And again, another hit point here, because we have decided to move right, and move right, move right, move right, move right, and we found the M line. And here we found the M line. We need to measure if this distance is smaller than this distance. Because if it is smaller, then we will get the goal. Okay? What happens if instead of turning right, we turn left? Approximately the same. We reach the same exact point. We store that as a hit point. We follow the obstacle until reaching again the M line, because the M line, the distance from this new point with the M line is smaller than the previous one, and then we just move towards the goal, then we move to the other side. Again, this distance is smaller than this distance, then we move towards the goal. This time, moving left has been slightly shorter than moving right, okay? But in both situations, we have reached the point. Let's see what happens here. That is when problems happen. Okay? Previously we had problems moving left. Okay? With the back zero, problems moving left. Let's see now what happens. Let's draw for the M line. Okay, this is the line. And now let's follow left. We move here, okay, we need to follow left. Okay, we reach a hit with the line and it's closer to the goal, then we just move around here. We start following the obstacle. This is going to take a while. Follow the obstacle, follow the obstacle, follow the obstacle. Here we reach again the M line. But remember that we have left the M line here. Is this point closer to the goal than the hit point? It is not. Then we keep following the obstacle. Again, another point. Is this point closer to this one? It is not. Then we just keep following, we just keep following. Following. Again, we cross the M line. Is this point closer than this one? Yes. Oh, yes. Then we move to the goal. You have seen that although it's not the best scenario when we decide to move left, we have reached the solution. It's the best path. It is not. It found the solution. It found the solution. Then, similar than in part 1, the part 2 is not complete. It's complete, but it is not optimal. Okay? And if we want to check a little bit the bounds of this M line, here it's not so easy to see it like in the previous bar, but the lower bound is exactly the same. we have no obstacles, we will just follow this M line, that is the minimum distance between the start position and the goal position. Otherwise, what we need to measure is how many times PI is the perimeter of the algorithm, and NI is the number of intersection points between the M line and the I obstacle. For instance, here we cross the perimeter 1, 2. And here we cross the perimeter 1, 2. Then 2 times here, 2 times here. Then the upper bound tells us that is the minimum, the distance between this and this, plus the sum, we need to add the number of polygons times the number of intersections per polygon. Then this is the number of intersections per polygon. This polygon, we have 2 intersections, times the perimeter of the polygon divided by 2. Then at least 1 time this polygon. In the other case, in the case that I draw here, we have 1, 2, 3, 4 intersections. You see? Then because we have 4 intersections, it's 4 times the perimeter of this divided by 2, then 2 times. We have not done 2 times, but we have done a little bit more than 1, because you see this part has been done twice. Then, yeah, it's an upper bound, okay, it's pessimistic, but it's what it's what the numbers say. Okay, it's fine. And this is the back two. And here the back algorithms more or less finalized. And these are the most popular ones that you will find in the literature. However, any of these 3 back algorithms you will find it nowadays implemented on a robot. The one that you can find implemented on a robot, well, this is a small exercise that I have for you later, is the one that we will see, the tangent. Okay, but sorry, I wasn't remembering of this exercise. Which algorithm do you think is best for each one of these 2 environments? Best, I mean faster, that found always the solution, etc. We have seen that here, probably the best one was back 0, no? Because it goes very fast. It's not the optimal one. The optimal will move here, here. And the optimal, I can show you, will be done something like that. I think there is no shorter path than this path to reach the goal. And the goal, the path 0, if you remember, was doing something like that. It's not so far to the optimal, more or less. Then, for this particular environment, probably path 0 will work. For this, okay, we can try to measure how many intersections we have. Now we have 1, 2, 3, 4, 5, 6, 7, 8 intersections. Divided by 2, it's 4 times the perimeter, while back 1, if you remember, was 1.5 times the perimeter. Then in this particular scenario, back 1 can be better than back 2. Okay? You can try to draw it. This is a good exam exercise, for instance, things like that. But, okay, it takes a while. But this is something that you should be able to do. As I told you, if you try to program, it's very nice. It's something that we will not ask you, but if you want to do it, it's okay. I think it's something that will help you to be better programmers in this kind of algorithms. But to understand the algorithms and be here and be able to do a back 1, a back 2, a back 0 in this particular case, that is not easy. This is something that you should be able to do. Okay, if you have any trouble, just tell me. Then at the end of the class, if you have time, we will do some exercises. Okay, here it says, no, back 1 is an exhaustive search algorithm. It looks first to all choices. Back 2, it's greedy algorithm. It takes the first thing that looks better. This is the normal thing. But for specific scenarios like this one, the one can be better than the other. We never will know that until we analyze it. Okay, then let's go now, yes, to the tangent back. Here the idea is to relax a little bit this constraint that the only sensors that we have are contact sensors, and assume that we have range sensors. Okay, that we can measure distances not just when we are touching almost the wall, but at some distance of the wall. Okay, here in back 0, 1, and 2, we just use global heading and this contact-based sensing, while real robots used to have range sensors, and then Tangent Book will make use of this range sensor. You can say the acoustic rangefinders, LiDAR, depth cameras, whatever you need. Just first concept, okay, to understand a little bit the drawings that I will be putting right now, because otherwise it's not easy. Here, this is X, this is the robot, and X is the position of the robot, okay? It's not XY, no, it's X contains the full state of the robot, XY, theta, whatever you need. This circle here, this circle, this is the range of our range sensor, okay? It means that we can measure distances up to this distance. And then if we can measure distance up to this distance, probably just imagine a LiDAR sensor, right? Something like that. Just, right? Then we end up measuring that there is a wall here, that there is another wall here, that there is another wall here, and then there's another wall here. Okay, here in this algorithm, we are more interested in these discontinuity points, what I've put here like 01, 02, 03, or 4, or 5, than with the wall itself, okay? We will be focusing on these points, on this. This will be like our obstacles, is this discontinuity points, okay, or this discontinuity intervals. Then, we will have again two behaviors. This is why it's still, although it's very different, it's why it's still called back, because it follows the same schema of if we have nothing around us, we just move toward the goal. If we have something in our sense area or range area, we start following some way the obstacle. Okay, in the green position, for instance, this is the range of the sensor, and we don't see any obstacle, then we just move forward. However, imagine here I've done a very large step, just to make it easy to see, but in this other step, I see this is my range area, and these are the discontinuity intervals, the 1, 2, 3, or 4. And here, we need to change from motion to goal to boundary fall. It's exactly the same ideas than we had before. However, here, the algorithm is slightly different. First of all, we need to see which of these points or we want to follow. To start following the boundary, we will put, imagine that if we want to follow from 01, then we will do something like that. If we want to follow from 02, we want to go close to 02 and then go through this obstacle instead of through this one, okay? But which one I have to select? Okay, then here I need to compute the distance from the goal to the robot. To the goal for the robot, this is the distance. Q is the current position of the robot. Q goal is the position of the goal. And then for each one of these 01, 02, or 3, or 4, whatever, check if the distance between them and the goal is smaller than the distance of the goal or not. If it's larger, for instance, 03, well, I think here all are smaller, maybe 04, I don't know. Imagine that this is larger, that this was one here, I don't know, that we have something like that, and here we have another discontinuity point. For sure, this point will be farther than the goal than the robot, okay? Then we will just discard them. But for all the rest, the one that we will choose, for the ones that are closer than the robot, is the one that we will choose the point that adding the distance from the robot to this point plus this point to the goal is the smaller. Then this plus this is smaller than this plus this. Okay, this is the one, the obstacle or the point or whatever that we will choose. In this case, I think that the smaller one is the O2. Okay, in the figure, this one from here to here, this is the shortest point that moving from here from the robot to this point and from this point to the goal, this is the shortest point. Then we will select O2 and we will start following this obstacle. Okay, our robot will try to do something like
it was coming from here, now we will try to follow this obstacle.
However, up to when we have to follow this obstacle, because what may happen is that the obstacle has some convex shape or something, and we can start getting far and far and far and far from the goal. And this is not our idea. We want to be close to the goal. Then to avoid that, to avoid moving far from the goal, we will compute two distances. Instead of only, remember that before we were just computing, when we were going through the full perimeter of the obstacle, we were measuring for each point the distance between this point in the perimeter of the obstacle and the goal, no? This d-min. Now we will compute two distances. I think they are here. Yeah? The first distance that we will measure is for each point that we can sense with our range sensors in the perimeter of the obstacle. We will measure the distance from B7 to goal, B6 to goal, B5 to goal, etc. All the points to the goal. And we will store the minimum position, okay? This is the minimum, the minimum d-min. The d-min I have the smallest distance from one sensed point to the goal sensed so far among the boundary points B of the current obstacle that we are following, no? The one that we are following. This is one thing that we have to measure. The second thing that we have to measure is the d-lift. And d-lift, it's a little bit more difficult maybe to see. D-lift, it's not straight distance like here, but d-lift at the current pose Q is the best optimistic two-segment distances is from here to here and from here to here. Okay? And as you can see, the second distance is tangent to the obstacle. It means I know that from here to here it's free because my range sensor is not measuring any obstacle in the middle. And from here to here, I can generate a line that is tangent to the obstacle and goes straight to the goal. Of course, I don't know if here this is. I don't know if the obstacle is here because I don't sense that. But from my point of view, right now, this it's free and this is tangent to the goal for what I see so far. Then this is my escape point, is my leaf point. The moment in which the leaf distance, this plus this, is smaller than this, then we stop following the boundary and just move towards this point and try to reach the goal. It's not so easy to understand this one, but in the end, it's totally
So curious, how was the visible point determined in the d-lift?
Yes.
I want to before the robot detects the visible point. I need to detect the parallel obstacle. How?
What do you mean? You need to detect d-lift. You know that this range here is free because your sensor do not return any contact point. Then it's free, and then you know that from any point in this, what you can measure is for.
I know where the goal is. This is some information. Remember that. This is some information I have. Then I can measure from this point that is free. I can go to the goal. No, because I collide. From this point that is free, I can go to the goal. No, because I collide. Because I know that all this is occupied. I have here this point.
I draw here very little obstacles, but you have to assume that this is much dense.
It means the signal, the sensor, the response is infinity.
Infinity? What do you mean infinity?
The signal.
The ranges?
Yeah.
What happens with the ranges?
I think it's don't respond when the signal sends.
Do you mean when there are no obstacles, you don't have a response from the sensor?
Yeah.
No, you have a maximum response. These sensors, if it's LiDAR or it's sonar or whatever, they have, for instance, the most simplest to understand is the sonar one. They just emit a sound
and wait for 1 second, no, not 1 second, a few milliseconds to receive the answer. If they do not receive nothing, it means that there is nothing in this path, and therefore that this is free. If it, of course, it may be that it's something, but it's something that absorbs the energy and you don't see it, but then you will crash it because you will not detect it. If they do not answer, then they always return or normally the maximum range. If, for instance, the maximum range of this sensor is 10 meters, then they will tell you 10 meters. Then up to 10 meters, there is nothing. After 10 meters, I don't know. But this is, sorry. And then the idea of computing that is that you measure here and you collide here, okay, here, maybe I will not collide. For as far as I know, here there is a tangent line that can bring me towards the goal, because I don't know if there is some obstacle here or not, but I can go it. Then it's a little bit tricky to compute this. The DMIN is quite easy, the DLIF is a little bit more tricky to compute. But in the end, it's very similar than the other back algorithms. You have two behaviors, motion to goal and boundary following. When you initiate this boundary following, you need to do this computation at which boundary exactly are you going to follow, because here you don't see only one single boundary, you can see multiple boundaries because you have a range sensor. And then whenever you are following the boundary, you just need to be computing all the time these two values until this condition match, and then you stop the boundary following and go again to the motion to go.
I have a question that, like, you can switch to the reverse. Previous.
Yeah.
Like if I have a equation here, so like the n visible point, how can we, for example, like the robot in this position?
Yes.
Then how we can know we can determine the visible point n from this, like, because the sensor there are no obstacle in the sensor range, like for the DLIF.
Yeah, here there are nothing in the sensor range.
So information they receive will be maximum. So but
yes.
How can we know the position, the pose of the visible point?
The point of which point?
Pose of the current visible point n.
Here, at the current pose Q, best optimistic two-segment distance be at a currently visible point. Okay, this is all points in this line are visible.
Yeah.
All these points that I draw here as circles are visible. Because if there was an obstacle here, you should have a return here. But because you don't have any return till the maximum range of the sensor, all these points are visible.
Yes. But like in just one ray, we will calculate each visible point.
Yeah, of course, you have to discretize that, and you need to compute a lot of them.
Until the end of the maximum.
Yeah, exactly. Yeah. No, it's not fast to compute. There are tricks to compute it faster, but yeah.
Sorry?
Don't worry.
On the same slide,
Yeah.
this position, does it follow DLIF or does it
No, in this position, DLIF is bigger than DMIN, then we will keep following the obstacle.
Okay, so it goes towards B7 until...
Yeah, well, it will just keep following this boundary until probably it's something like around here, and then around here you will measure a point that just the DLIF will directly, in this case, will directly touch that and will be much faster this than than the minimum distance from here to here.
Okay.
I mean, this is an example, animated example that I've implemented. Here I mark all of these points and these tangents and things. More or less is how it will behave, but the idea is that the moment in which it found it's following an obstacle, but you see that sometimes it's not going through the tangent, it's just because it has more than one obstacle to follow, and then it checks which is the obstacle, that the distance from the robot to the obstacle and the obstacle to the goal is better, and then it swaps from following this boundary to following this boundary until the very end, in which what is faster is this moment. In this moment, it's following that until there is a moment in which there is just a ray that goes directly to the goal that is much faster. Follow this ray, that is the DLIF, than keep following the obstacle. I mean, don't get obsessed with that. I will ask you to implement this algorithm for sure. Okay, what is nice of this algorithm is that if we assume that our range sensor is almost zero, then we have a very similar behavior than a back zero. Very similar. It's not exactly the same. In some situations it may change, but we have an algorithm that will be very similar to the D0. Of course, we lose all these advantages that the tangent book has. With a normal implementation of the tangent book, what we will have is that we have a finite sensor, 5 meters, 10 meters, 20 meters. This is the boundaries that we will follow, and then this is more or less what we are going to do. No, here we move forward, then we detect a point here, because the distance from this point to the obstacle is closer than the distance from the robot to the obstacle. We start following this obstacle, we start following, and at this moment, probably we see these two obstacles, and the distance from the robot to here and from here to the goal, or the robot from the distance from the robot to here and from here to the goal, this is smaller, then we swap, and instead of following this obstacle, we start following this obstacle, and we swap here again, and here we just have a lift. You see, here the distance, the minimum distance is from here to here, then is this distance from here to here. This is one distance, while the other will be from this point. Well, yeah, approximately it's from this point to this point. Then from here to here and from here to here, probably this is slightly shorter, and then it follows the D-lift. It just exits this obstacle, we goes here, we just follow this, and here it's following until we reach a point in which also it's faster just go directly to the goal than keep following this obstacle. Okay, I just want you to get the idea. I will not be asking you. If you see, there is no pseudocode in this algorithm, because it was impossible to put a shorter pseudocode for this algorithm. When the tangent book has infinite sensor range, and this may only happen if we know the environment. I mean, that we are not using a real LiDAR sensor or a real sonar sensor, but we just have all the obstacles. And then we can assume that we can see through the obstacles, it's an idealized scenario. It's not even that, it's not guaranteed to be optimal. Okay? We will be very close to an optimal algorithm, but it's not guaranteed. Mathematically, we cannot guarantee that we in some situations, maybe we just decide to turn for one side, and it should be best to be turning for the other side. Then it's complete, of course, it's complete. But even that we have an infinite distance, it's not guaranteed to be complete. Okay, and just summarizing Keynote. Here we assume that we have local sensing. It means that we don't know, except for this last algorithm, for this last environment, we assume this idealized scenario. We don't assume that we know the environment. We assume that we only know what our robot is able to detect in situ. This is important because you will see that for most of the other algorithms that we will be showing during this semester, we will assume that the world is known, that the environment is known, while most of the time this is not true. In the second semester, then we will relax this assumption, and again to return to the local sensing assumption, okay? But for most of the other algorithms that are a little bit more complex, then we will assume that the world is known. Here, no, we only need to detect what is in our vicinity, that's all. Then we don't require the full environment. We have always two behaviors in back algorithms, one that goes through the goal and one that follows obstacles. When we decide to switch from one to the other, it changes. If it's back 0, if it's back 1, if it's back 2, it changes, but they are always. And then the switching between behaviors normally takes in consideration the distance. When we have done the full row, then we move to the closest point and then we switch. Or when we have line of sight, we switch. Or whatever, we switch. But they are more or less following this schema. Okay. As I told you, it's very good for you. If you want, we can. Where it is already? It's if you want to do something like that at home,
it's very nice for you. I think I have also here some other, where is sorry, smaller, close this one, no. There is here some other box exercise. These are some examples, for instance. This is an exercise I put in an exam, in which I put these two scenarios, and for each of these scenarios, I ask the students to write the back 0, back 1, and back 2. Okay? I can upload that in the website if you want.
A question, this is not from this. You were saying that this semester we're going to work like knowing the obstacles, right?
Most of the exercises will be, yes, with a known map.
So in the code we will know like the distance between the first obstacle.
Well, there are a lot of different ways to represent the obstacles. This is what I'm going to talk now in 10 minutes. But yeah, or you will have, most of the time you will have the map, the full map. Okay? Okay, then what I was telling you, this is just kind of exam-like exercise that if you want, I will put it in Moodle and you can, I will not be asking you to deliver it, but I think it's worth for you to try it. And if you have any problem making it, doing it, just tell me. Okay? But okay, it's just try to follow using back 0, back 1, and back 2. As you can see here, I'm not asking you for tangent back because it's not easy to compute all the d-leave and d-mean and all this stuff. I will not do that in an exam, don't worry. But trying to follow and see if, for instance, for the back 0, if it's possible to get stuck depending on the direction that you choose, etc. Okay, I think I was asking for them to do it, except for the back 1, that is the same. The back 0 and the back 2 do it for both left and right options. Okay, then I will put that in the Moodle. And then, if you have time, I will back this last 15 minutes just to introduce this topic and then everybody will see open this. Draw board. Okay. Okay. The concept of the configuration space, well, it's not only the configuration space, but there is several concepts that are here. As I told you, it's more definitions that is worth for you to know than nothing else, okay? The first thing is, what is a robot configuration? In the previous example, I put X, and X means the full robot state. Sometimes we will put X, sometimes we will put Q configuration, okay? And this determines the degrees of freedom normally. It's determined according to the degrees of freedom of the robot. Okay? And degrees of freedom refers to that. The independent parameters need to specify the robot configuration. For instance, if we have a point robot, a robot that it's a point that has no space, let's say, it's an imaginary robot, okay, and this robot moves in a 2D area, our configuration will be as simple as xy. Okay, q vector will be, or x vector will be xy. I prefer to put q here because we already have the x here, then it's just to not confuse people. But in probabilistic robotics, you will be using x all the time for the state, then it's the same. Imagine that instead of a point robot, that is something that you will not find in the reality, we have a real 2D robot, a turtle bot, for instance. We will be working next semester. Then in addition of the x and y, we have the theta. Okay, as I told you, sometimes you will see theta, sometimes you will see yaw. Okay, it's when we use the 3 rotations in x, in y, and in z. The rotation in z, that is the one that affects the 2D, it's called yaw, and then we use this letter. Otherwise, sometimes we use just the theta. However, if we have a drone moving in the 3D world, then it's not enough x, y, and theta to represent it. What we need is x, y, z for the altitude, and then the 3 rotations. And normally we don't like a lot to put the Euler angles. And instead of that, we will put our rotation matrix, rotation matrices, or quaternions. Or you can also use the algebra. But the algebra, I don't know if Pere will explain you a little bit about, but
I'm not going to use it in my courses, okay? But rotation matrices and quaternions, that is what is in the ROS libraries, especially in the second semester when you have to really program the robots, you will see that we don't rely a lot on angular angles. We prefer to use or rotation matrices or quaternion matrices. And what happens if you have an industrial manipulator? Then it's a little bit more difficult because you can specify just the position of your n effector like a drone with an x, y, theta and a rotation, or you can just specify the position of each articulation. This is another two different ways to specify the configuration of an industrial manipulator, or an industrial manipulator, or any robot that has arms or legs or something articulated. Okay? Then the Q represents that. Then a little bit more of terminology. Okay? The space, the configuration space, C space, is the set of all possible configurations. Okay? If our robot has only x, y, theta, then the configuration space is the combination of all possible x, all possible y's, and all possible thetas. Of course, this is an infinite number, okay? Although, because we are programming the things, we are working with robots, in the end we will discretize that at some point. But the C space, it's all possible configurations. And inside this set of all possible configurations, some of them will be valid, and some of them will be invalid. The ones that are invalid, for us, will be the ones that are in collision with an obstacle. And the ones that are valid will be the ones that are collision-free. And then, how we know if there is an obstacle or if there is not? Because we have a description of the wall. Okay, the description of the wall, here I put W. And this is what can be very different. Okay? A description of a wall can be just, imagine that I decide that all my obstacles in a 2D wall are circles, and then the W is just a list that says the X, Y, and radius for each circle. And what is inside the circle is an obstacle, and what is outside the circle is free. This is a perfectly fine description of a wall for a 2D environment. Another one can be a matrix. I can just take a matrix and decide that each cell in the matrix belongs to 10 by 10 centimeters in the real wall, and then if the cell has 0, there are no obstacles. If the cell has a 1, there are obstacles. In the end, this is a map. Okay, it's a map at the 10 by 10 centimeters resolution, and this can be used to define what is free and what is occupied. And I can have also, I don't know, a collection of meshes. Mesh, 3D objects, and depending on the triangles of this mesh, if it's inside or outside of this mesh, decide if it's a collision, or if it is in collision or not, etc. There is plenty of ways to define the wall. Okay, and depending on the problem, depending on what we are doing, we will use one or the other. Most of the time in this course, we will use just a matrix. Okay, a matrix in which each cell in the matrix it's a position in the wall, and it can be free or it can be occupied. This will be our most common way to express the obstacles in a wall, but the other, a list of obstacles, it's something that in some very simple examples we will use it. So, then, here I see that I don't have it, but normally what we have a function that is called isValid or something like that, in which we pass the W, and we have a robot configuration, I put here a robot description at a particular configuration. And then this returns if true or false. Okay, is valid to have this description of this robot in this particular configuration, in this particular wall? Why we need all these elements? The robot configuration tells us where the robot is. But it is not the same to have a very small robot here that has a very big robot here. Okay, if the robot is very big, maybe it will not fit this position here. Therefore, the A told me exactly how many space this robot occupies in this particular configuration. And then the W will tell me if in this area there are obstacles or not. And in the end, the is valid function will just compute all of this and return a true or a false, okay? And this is a function that you will have to implement and you have to understand. Finally, if it returns true, it's because the robot, this configuration, belongs to the free space, the free configuration space for the robot in this particular wall. If it returns false, it's because it's in the occupied space. Okay? For some particular robots, for instance, for a punctual robot, a robot that is just a point, the description of the robot, especially if we use a map, and what is free space and what is occupied space is exactly the same. It's very simple to compute, we don't have to do nothing, it's very simple. However, if we use a little bit more realistic robot, like a Turtlebot, that is what you are going to use mostly, the description of the robot and the description of the wall and the free space or the C space that we can use, no, the valid C space that we can use is not the same. In this case, you can see that if the robot has this shape, then what we can go is to all the white positions, but not to the gray ones, because although the center position will be free here, the robot, let me do it. If I draw here, if I put this robot in this position, although this position seems valid because the robot takes all this space, the robot will be in contact with the obstacle. Therefore, what I need to do is just to increase the size of the obstacle in a way in order to allow that if I put my robot here in this corner, in fact what I'm doing is putting the robot exactly here. Almost touching all the obstacles, but not in direct contact with the obstacles. Of course, if my robot is bigger, then I already have less free space or valid C space. When your robot is a circle, this is very easy. When your robot is a manipulator, or it's a robot that, depending on its orientation, has one shape or another, it's not easy. Okay, to compute it. Sometimes it means that we can pre-compute this valid space, and then this accelerates a lot our computations, but sometimes no. But why we need that? Why we need to know that the space is valid or is not valid? Because this is the goal of all these lessons is always the same. The goal in the motion planning for us is we have a robot in an initial position, we want to reach the position, we know the configuration of the robot, all the possible configurations that it has to follow, and we know the description of the wall, that maybe there is an obstacle here, there is an obstacle here, there is an obstacle here, etc. And in the end, what we want is to check that all the configurations that we need to pass to go from this initial position to this go-up position belong to the C-free, or the C space that is valid, okay? In some books you will see C-free and C-obstacle, in some just C space as the valid space that the robot can reach. Okay, then this will be our goal. There are ways to compute this C-free space that if we can do it beforehand, then it will be much faster for us to do all the computations. And basically, there are two main families to do that. One is the geometric methods, and the other are the approximated methods. We're not going to use the geometric methods. I just put you here one reference if you want to check them. That is the Minkowski sum. And in this method, this was popular in the 90s, very time ago, okay? Several ways, clever ways, mathematical ways that if you know the shape of your vehicle and you know the shape of your obstacles beforehand, because you know the wall is known a priori, then combinations how you need to compute this extra shape, how you need to increase the size of your obstacles in order to make to compute beforehand this C space and then make all the computations faster. Okay, there was lots of research in the 90s on this topic. However, we are not going to use that. We are going to assume, because it's in the end we don't want to stuck ourselves in a world that is very well known, that never changes, that is super static. We are in a field robotics master, and in the field robotics, the world changes, the world is dynamic, and then we are trying to focus more on these other methods, in which we define our world, as I told you, as a matrix, in which, or a grid, if you want, in which some cells are occupied, some are free. There was people also in the 90s that instead of using grids, were using more cell decomposition. We are not going to use much of cell decomposition. We are going to use grids. And from these grids, for instance, one method that is still being used nowadays is just a very simple one, which is just, this is our robot. As you can see here, this is the robot. Okay, then let's imagine the circle, the minimum circle that contains the robot. And then for each obstacle, obstacles are these red dots here. Then for each one of these obstacles, let's grow one of these circles around it. And that's all. And with that, we can very fastly grow the obstacles that we have just detected in a grid environment. If you can see here, maybe in the distance you cannot see very much, but this is not a continuous drawing. These are cells, are small cells. I don't know if 5 centimeters or 10 centimeter cells, but they are cells. Then, okay, I know that these cells contain an obstacle. Okay, then let's make just all the cells that I can fit a circle around them occupied, and all these blue areas are areas that I know that I cannot reach with my vehicle. Okay, and this is a fast way, and that is already implemented in ROS, for instance, to compute the C-free space for your robot. Okay, I know that this is something a little bit out of nowhere, very different to the VAC algorithm, but it was basically to introduce the concept of configuration, of wall definition, or obstacles, of the C space, and how we can compute this C space, this value function, and all this stuff, because they are things that we will need for the rest of the course, and they are just these 10 minutes, 15 minutes, and I take profit today that we finalize a little bit earlier to explain it to you. Okay, then if there is nothing else, there are no more questions. See you next week. And now I think Sebastian will come here and we will start the class.